Hello everyone, we are back. We are talking about effect size, and we're also going to be talking about alpha, beta, and power in our new quick tutorial on, wait, what am I doing? Remember, these are meant as supplements to what the work we're doing in class, but it gives you an opportunity to kind of check back in, check if you're doing things right, to kind of get those reminders while you're working on homework and while you're studying. So, the first thing that I want to remind us about is the reason that we do measures of effect size. We measure effect size in part because we have concerns about hypothesis testing. When we're doing hypothesis testing, oftentimes we have kind of a binary decision. Yes, we reject the null, or no, we fail to reject, right? We have this yes-no situation. We can't do both. It's an either or, and it really focuses on the data. It's not really focusing on the hypothesis. And so just because we're able to reject a null, we might get a significant effect, but those effects may not be very large. Those effects might be very small, or they might not necessarily be meaningful. They may not really be a big difference it's not a practical significance. It just might be statistically significant. So effect size is our tool against this. In addition to this yes-no binary decision, we get information on a continuum with an effect size. We can get information about a small effect size, we can get information about a medium effect size, we can get information about a large effect size, and we can get this number tells us this magnitude, is it small, medium, or large, of this treatment effect. And it starts to take sample size out of the equation. And so we're getting a better picture of what's going on than we would with hypothesis testing alone. Hypothesis testing is still important. We're still going to use it again and again and again and again in this class, but it's not enough. And so we want to make sure we're adding this measure of effect size. When we're doing z-scores, really our main option is Cohen's d for a measure of effect size. When we get to other kinds of statistical tests, we'll continue to have Cohen's d, but we'll have some other options as well. So the benefit of effect size is this gives us a standardized way to compare effects across study. Because it's not as reliable and not as reliant on sample size, and it's more objective, we can compare these between different studies. Okay, in this study I saw they did all of these different things, they measured it this way, and they got an effect size of 0.5. They did this they were interested in similar kinds of things over here. They measured it completely different. They did these other things, but I'm also finding an effect of about 0.5. Again, this allows us this standardized way to compare this measure, this effect, between different studies. So, Cohen's d, here's our formula for Cohen's d. Note there's a couple of things about this formula. One, oftentimes we don't actually have the parameter for the treatment. What we're going to be using is that sample mean to come up with that estimation. So we'll oftentimes use that sample mean instead. And also note that this is standard deviation, not standard error. So this is standard deviation here. This is not standard error, so you may have to recalculate something. These are our conventions for small, medium, or large. Again, they're on a continuum. So if you're somewhere between 0.2 and 0.5, you can use things like relatively large, or relatively medium, or small to medium effect. You can use these kind of in-between terms because that's the benefit of effect size, is we are a continuum and we're not this either-or kind of situation. Notice that this is magnitude, so it's independent of whether it's plus or minus. So I can get a negative value of 0.8, and that's still a really large effect. Even though it's negative, we're like, oh, well, that's tiny then. No, it actually means that there's a really big difference. So the magnitude doesn't matter here at all, whether it's plus or minus doesn't matter here at all. What matters is this value on this continuum. So to kind of practice how we calculate those, that's why I pulled out this annotation, is so that we can do these. Again, here we're using these population parameters, but if you don't have the population parameter, you would use the sample statistic to estimate it instead. So either one is fine depending on what information you're getting. So here it says this is after treatment. So this is the first value I'm going to do. So my 515, I'm going to compare that against my 500 here. And I'm just subtracting those and I get a value of 15. I'm going to divide that again by my standard deviation. My standard deviation here is 100. And when I do the math on that, I get a D value, a Cohen's D of 0.15. Remember, by our convention, that would be a small effect size. It's less than 0.2, so we can pretty confidently say this is not much going on here. Now, for our second example, we still are going to end up with a difference of 15 on our numerator. But because we have much smaller standard deviation here, we're going to end up with a D value, a Cohen's D of 1, which would be a very large effect, right? And so again, by standardizing this, by pulling sample size, by pulling these measures kind of out of it, we're able to get these kind of comparable things. These are being scored very, very differently. 500 versus 100. These are very different scales of measurement. And again, Cohen's D is standardizing this way that I can say, oh, well, whatever the treatment is for IQ is, probably better than whatever the treatment is for this SAT scores, because I'm getting a much bigger effect here than I am getting here. And again, I'm allowed to make those comparisons because measures of effect size are standardized in that way. To do our recap on alpha, beta, and power, remember we oftentimes have these real world situations that we don't know. We don't actually know in the real world if the null hypothesis is true or the research hypothesis is true. But because we don't know and we're making an inference based on this decision here, this decision is our inference about the population, we can have situations where we make errors, right? So we can have a situation where we reject the null and we support the research, right? And in this situation, we could have a situation where the null hypothesis is actually true. In that situation, we've made an error. The type of error we have made is a type 1 error, where we are saying there's an effect when there's not really an effect. And we really don't want to make that effect, and it's the one kind that we have control over, so we get to set that value with alpha. So alpha is the probability of making a type 1 error. Again, we get to set that, and we typically set that at 5% or 1%. Those are the risks that we're willing to take of making a type 1 error when we're supporting the research, we're rejecting the null when the null hypothesis is actually true. Again, we don't know what's happening in the real world. We're making these inferences, and we don't want to make these errors, so this is our risk. Now, we can have the situation where we reject the null and the research and support the research, and the research hypothesis is actually true. And this is the goal, right? This is where the magic happens, and that magic has a name. That magic is called power. Power is our ability to find an effect that is actually there, to support the research hypothesis when it is actually true. It is going to be calculated by subtracting beta from 1, and what is left is the probability of power. Typically, we like that at 0.8, but we don't always have as much control over that as we would like we do with alpha. We can also have the situation where we fail to reject the null, and the null hypothesis is true. That's good. Right? We didn't reject the null. The null hypothesis is actually true. We've again made a correct decision. Remember, we're going to never accept the null though, because it could still be an error. So we're going to fail to reject the null. Null effects are really hard to find. The idea of no difference is really hard to find. And so while we might be making a right decision, we don't necessarily know that real world situation. And so that's why we're going to never accept the null. The last kind of error we can have is our type 2 error. This is where we fail to reject the null and the research hypothesis is actually true. We said there's no effect, but there actually is an effect. and that is called type 2 error. The probability of type 2 error is beta. This is that same beta that we were talking about up here in power. So when we set alpha, that will influence beta and power depending on kind of how big of an effect size we have. So again, alpha is that probability of making a type 1 error. We usually set this at 0.05. Beta is the probability of making a type 2 error. Power is our ability, which is again, the goal is to be able to find an effect that's actually there. And again, we typically aim for that 0.01. Because beta and power are on the same distribution, if we have beta here, then this side would be power. And so we're going to see kind of no matter where this line goes, the left side will be beta and the right side will be power. As promised, here are those graphics that kind of walk us through that. So here we have two distributions. We have the mean of distribution 1 being greater than the mean of distribution 2. So you can see this value is further along on this number line than distribution 2 is. So we have this value is greater here. This is going to be actually a pretty large effect size. So we're going to have our comparison distribution. This is what we're making our decisions about. This is where we're setting alpha. This is where we're putting our scores. This is all of that thing. And we also have our distribution of means for population 1. This is the means when the research hypothesis is actually true. This is what we don't know, right? We don't have necessarily access to this. So this is where beta will be, this is where power will be, but we don't have the control of setting those. And our effect size is, again, the difference kind of between the two means. You can see that that difference is there. So we've got a pretty good effect size there. And alpha is where we can set our cutoff value. And so that is always going to be on that comparison distribution. That distribution that we have control over is where we're setting alpha. When we're setting alpha, we subsequently influence beta on the other distribution. Here I have these distributions on top of each other. On an assessment or on an assignment, I'll separate those distributions out for you so that you can kind of see them not on top of each other and can shade them in easier. So alpha and beta are on opposite sides of the line. If alpha is our risk of making a type 1 error, and beta is our risk of making a type 2 error, when we set alpha, it subsequently influences beta on the other distribution, right? And this is where we have the research is actually true, but we aren't able to reject the null and we fail to reject the null. So this would be a miss. And here we don't have a lot of risk of making this type 2 error because our effect size is so big. This also means that we have a whole bunch of power, which again is our goal. We want that power. And so we have a lot more power here because this effect size is very large. Here we have another scenario. Again, we're going to have the same situation where mean of population 1 is greater than the mean of population 2. We have our comparison distribution where we're setting things. We have our distribution of means where the research hypothesis is true. But here we have a much smaller effect size, right? We have a lot more overlap between these distributions here. And we're going to see how that will influence our beta and our power. So it's going to be a lot harder to find this effect because it's smaller. Think of it like a diamond versus a teddy bear than it would be another. So we get to set alpha on that comparison distribution, but look what that does to beta here while we have this smaller effect size. So here we're going to have a lot more risk of making that type 2 error, even though our risk of making our type 1 error is the same. We can still have a 5% chance, but because we have this smaller effect size, we're going to have a lot more opportunities for misses in beta. Our power is also then diminished. And so we won't have as much ability to say there's an effect when there's actually an effect. So that ends our conversation on alpha, beta, power, and effect size. I hope this was helpful. Thanks.